Okay. All right. First question, would the mobility be affected severely SOI due to the interface below the channel? Okay, as far as I know, for thick SOI, the mobility is not very different from bulk. But for very thin SOI, like thinner than 5 to 10 nanometers, then the mobility could degrade because the back interface is too close to the front channel. Okay. Next question, refer to this chart. There's a back gate VBG. What's the main purpose? Well, there's a substrate that's called a back gate, and so the bias have some effect. It depends on how thick the buried oxide is. Okay, well, we will derive some equations relating the effect of the backgate bias on the threshold voltage. This is kind of like in the bulk MOSFET. You have substrate sensitivity. In other words, if you for bulk, let's go back to for bulk case, there's the substrate beyond the maximum depletion depth, and if you bias there, that will affect the VT. Okay, so it's a similar effect. And in some circuit, they may use the VBG to change the threshold voltage on the front gate. Okay, but it needs to be very high gate voltage. Okay, we will go over that pretty soon in chapter 7. Okay, next question is gallium nitride. Excuse me. High breakdown voltage. Okay, I think the key answer is that the very wide band gap, 3.4 eV. Okay, and let me show you this chart I showed in the beginning in the first class. Okay, you can see that the gallium nitride 3.4 eV is almost like an insulator. Very close to the 4 eV mentioned here. And so the breakdown voltage depend on the band gap, because for impolarization, you have the electron has to be energetic enough to produce electron hole pairs, which means that the energy has to exceed the band gap. So if band gap is very high, then you take very high voltage for this breakdown impact ionization to occur. Okay. Next question is about this chart, which I add this. I say that missing the last part. Okay, so in this picture, there's nothing under the box, but of course there's a substrate, or we call it a backgate. In this, see the same thing here. Okay, so I add this label substrate backgate. The last question I cannot answer, but Sun Yanzang, who cannot be here today, but he will be here next Monday, and he will address this question when he goes over the next part on November 4th. Okay, so that's all the questions. Let's go back to chapter 7, where we had, let's see. Okay. Andy, so you see the SOI chart?
Yes.
Okay. So we covered the in the last class. At the end of last class, we said that we draw the Venn diagram and define the potential with reference to the n plus source Fermi level, this dotted line here, and then we can actually solve the equations with the complete solution is here. The potential, the two Poisson equation, assuming that there's no depletion charge. Okay, so this is all electron charge, no mobile charge only. Well, I will justify this later. And the solution is here, which involves two constants, E0 and V0. And so they are solved from two boundary conditions. One for the front side, the field and the potential here. The potential drop across oxide is related to the field at the front surface. And the second one is the backside. Also the potential drop across the back oxide is related to the field at the backside interface. Okay, so basically that side. And this, even though it's the differential equation solved, but to solve the two parameters, we have two implicit equations. So that has to be done numerically, okay? Unless we talk about subthreshold, which we will go into later. Okay? But first, let me address a conceptual question. So we assume that the silicon in SOI is undoped. Well, first of all, what about it? What about the Fermi level? There's no contact to silicon to the silicon body in SOI. Okay. So the answer is that, let's see, go back to here. I go back to this schematic. So consider this SOI, fully depleted SOI in the case in the middle. There's no contact to the silicon between the source and, well, there's a contact to the source and so on to the drain, but no contact to the p-type or undoped silicon region in between. So the Fermi level of this region is determined by the Fermi level of the source and drain. Okay, so assume that the source and drain, there's no VDS. VDS is equal to 0. And of course, source and drain have the same Fermi level, and there's no current flowing. There's no drain bias. Doesn't matter what gate voltage is. And so the Fermi level in this case is the same Fermi level as source and drain. If drain has a different Fermi level because we apply VDS, then Fermi level in the SOI body is determined by is somewhere between the source Fermi level and drain Fermi level, such that the current continuity equation is satisfied. So let's go back to the chart. This chart. Okay, so it's dictated by the source and drain Fermi level. But from chapter 2, the first thing in chapter 2 is we say that the psi b is K over Q, NA over N. Of course, in this case, we say it's undoped, but actually, it cannot be undoped because it's just too pure silicon to make. So there is some low level doping even if you try to make silicon the purest possible, there's some impurity inside. So the best you can do maybe 10 to the 14. Okay, so there will be some doping, which may be p-type or may even be n-type. So what about the psi b condition? And this is based on the charge neutral condition covered in chapter 2. But that actually does not apply to SOI because for a thin SOI, unless they happen to be charge neutral, in general, it's not charge neutral. Okay? And simply because the Fermi level is not determined by this charge neutral condition, but rather determined by the source and drain Fermi level. Okay. And so for a silicon body, thin silicon body, it's like a region, like a p-n junction here. Okay. Outside of the depletion region, Fermi level is determined by the charge neutral condition, P and N. But in the depletion region, the Fermi level is not given by that, and it's not charge neutral. Okay, so for SOI, actually, there's some depletion charge in SOI, just because this condition is not satisfied. It's not always satisfied, right? Unless by accident. Okay. So what about band bending if it is not charge neutral? Okay. So this little simple calculation shows that the band bending is negligible. Okay, so we take the Poisson equation with the depletion charge. Let's say the Na is the doping of the SY region. We integrate twice. We have a psi equal to this x squared. So let's put in some numbers. If Na is 116 and x is 10 nanometer, then the band bending due to this charge, the depletion charge, is less than 1 millivolt. It's only 0.8 millivolt. Okay. So this means that even though this condition, so you can throw this condition away when you talk about SOI. And there will be some charge depending on what the residual doping level is, which can be 10 to the 13, 10 to the 14, or 10 to the 16, up to 16. But the band bending due to that charge is negligible. So this justifies the assumption that it's undoped. Okay, because even though there's a very light doping and the Fermi level is not charge neutral, but the effect of that net depletion charge over a very, the key is this only, X is only 10 nanometer. Okay? So it's because the silicon is very thin. So for this band bending to be large, the Na has to be like something like 10 to 18. Okay, and then you have something like 10 millivolts of band bending. Okay, even that is not that big. Okay, so as long as the doping is not much larger than 10 to 16, and the thickness of SOI is not much larger than 10 nanometer, we treated the silicon as undoped. Okay, so this justifies this model approach that there is electron mobile charge only with no depletion charge, which makes the differential equations solvable analytically. Okay? I went over that before in the last class. Okay, so if you follow this model, we can solve in general the potential as a function of x. Okay, I'll show one example in this chart. Okay. So the parameters are given at the bottom here. Okay. 2 nanometer oxide, 10 nanometer silicon, beryllium oxide 25 nanometers, which is not very thick. And the phi mi, remember the phi mi is the work function of friend gate with respect to intrinsic silicon. Okay, let's go back. See, okay. So that's phi m is the gate work function. And what goes in the boundary condition is phi m minus phi si. Si means the work function of intrinsic silicon. Okay, so we call this phi mi. Okay, and for the backgate, we have a backgate work function, again minus intrinsic silicon, and we call this phi bgi. Okay, so you can see that it comes in here, the boundary condition, phi mi, phi bgi. Okay. Now, what we want here, what we are plotting here is qi. The key parameter is qi. Qi is this line. This is the solution. This is surface potential. The potential at x equals 0. Again, let's go back to that. The potential at x equals 0 is the friend surface, the surface potential on friend surface. Let's see. That's this curve. Okay. And the other curve, this curve, is qi as a function of gate voltage, based on the solution that we just mentioned, based on this numerical solution for these set of parameters. So after we get the potential as a function of x, how do we get qi? Okay, we use Gauss law. Right, so basically qi in the bulk case, remember that in the bulk, qi is related to the field or the displacement at the friend surface. But for SOI, you have two terms. You have the displacement on friend surface and also displacement at the back surface. Friend surface x equals 0, back surface x equals to T silicon. And the difference between these two is qi. That's basically Gauss law. In bulk, you don't have the second term because the field at the boundary of the depletion region is 0. So you only have one term. In this case, you can have two terms. Notice that if so it's a difference between the two displacements or the slope. If the slope are the same, then qi is 0. Okay, so if you go back here, right? So basically it's the slope or the displacement on front minus displacement on the back. Now, if this is constant field, then there's no charge, okay? Because even though d psi dx is non-zero, but the curvature is 0. The field is constant. But when the gate voltage make the surface potential close to the conduction band of or the Fermi level of m plus, then you have charge. In that case, you will have a qi. So basically, we are trying to calculate this qi through the solution, and that's given by based on the boundary condition. Okay. It's the potential across the friend oxide divided by multiplied by Cox, and the potential drop across the box or back oxide multiplied by the capacitance on the backside. So, okay, let's talk about a couple of things here. First, we notice that the QI indicates that there's some kind of threshold voltage near 0. Okay? That's because front gate is N plus. Okay? And okay, now here we can generate a curve, but how do we define threshold voltage? Okay, and so let's go to this curve. This is a solution for the surface potential. So we can see that okay, this cross indicate Eg over 2q or 0.56 right here. Okay, at this point, we go back to the Venn diagram. At this point, okay, the intrinsic level, okay, the intrinsic level is Eg over 2 below EFS, which means that the conduction band is touching the source, N plus source Fermi level. So of course you have a lot of electrons here. Okay, so, but in fact, you already have emerging charge starting to go up before we get to this cross 0.56. That's the extrapolating this line. Below something like 0.44 or so, that's a straight line. We talk about that. This is so-called a subthreshold, in which case we can actually solve it. But so so physical interpretation is that once the front surface conduction band is close to the source Fermi level, then the MOSFET or the emerging charge goes up, shown by the second curve. Okay? And so from this, you can see that the current starts to go up even before the front surface conduction band crossed the source Fermi level, about 100 millivolts before. But of course, when Vg keeps going up, then the surface potential will increase. We can exceed that, yeah, and that's given by this. Okay, we'll talk about this this threshold later. Yeah? But first, let's talk about subthreshold. Okay, this plot for this example is based on the numerical solution to the general model. Okay? But if it's in subthreshold, okay, that means the field is constant in silicon. In that case, it's very easy to solve. Okay, because the two boundary conditions. Okay, this field becomes constant. The constant is E0. Okay, front side and back side, they have the same value. Okay, and also the potential difference between the back and front is simply the thickness times the slope. Right? Thickness T silicon times E0. So when you combine these three equations, you can solve E0. Okay, basically you take the difference between the two, of the two. And the difference of potential is given by that. And then here we have That's also a multiplier. Okay, so based on these three equations, you can solve E0. Okay, and that's given by that. Okay? So mathematically it's strictly from this. This of course only valid in subthreshold. Okay? In other words, in here, over here, where the immersion charge is negligible. Therefore, essentially this is 0. Okay, so no curvature and field is constant. And then we can solve these two equations for the field. So that's how we can generate. Okay, so that's how we can generate the solution of E0 in subthreshold. Okay. And so we go back. So that's the solution here. And then we can solve for psi 0. Basically, once you know E0, you can solve psi 0 here. Okay. And that's the result. Where we introduce effect of M. This M actually has the same meaning as in the bulk. Okay, remember that in bulk, we introduce the M factor, which is the ratio of when you apply a differential voltage, gate voltage change, how much the surface potential change. The ratio is defined by M. Okay, so it's the same thing here. So M is defined by the change of gate voltage divided by the change of furnace surface potential. Okay? And the psi 0 is given by that. So we can solve M. And M is given by this in general, which is 1 plus that, which is exactly the same as, so in other words, if you use this for bulk and then interpret the edge of the depletion region as the substrate or the backgate. Okay. In other words, go back here. In other words, the distance, the dielectric distance from the front surface all the way to the backgate. Okay, that's serve the purpose of WDM in bulk. WDM is the depletion width. Okay, and so if you use that as WDM, then everything just follows. Okay? So you can see here that M is simply 1 plus front oxide divided by T silicon plus the back oxide. Okay, those are, of course, they have dielectric constant ratio and all that. Okay? Now, let's consider this factor. The T box M is actually very close to 1 because T box is thick, usually much thicker than the front gate oxide. Okay? If M is close to 1, then that means that the substrate swing is close to 60 millivolt per decade. Okay, the swing is M times 60, 2.3 kV is 60 millivolt per decade, and so that's good because that means that you have the ideal substrate swing at 60 millivolt for the bulk MOSFET. As we mentioned, we have to keep M not much higher than 1.3, which means that you start with 80 millivolt per decade or 78 millivolt per decade. But this is for long channel. Okay, so for short channel, we'll get back to the picture later. Okay? That's a different story. Okay, now let's get to the VT definition. Okay, let's go back to this chart. So how do we define VT? Here I give an example of we define VT as the gate voltage for the front surface potential equal to Eg over 2, 0.56. You know, it's this cross here. Okay, now if it looks like the actual VT is lower than that because the inversion charge starts to increase before the psi 0 is Eg over 2 here. But if you consider this and then you try to linearly extrapolate this green dashed line to here, that's actually higher than the when the inversion charge begins to go up. Okay. In this particular, I put down some numbers. In this particular case, M is 1.07. Okay. Okay. Now, first, if we define VT to be the gate voltage where size equal to half a band gap, 5.56. Okay, then we can put them back in here. Okay, and then solve. So we set this equal to Eg over 2. Okay, we can solve VGS, and that VGS is VT according to this definition. Okay, so from this equation we can derive this. So this means that VT is equal to the work function difference between the gate and the intrinsic silicon plus this M Eg over 2Q. M is close to 1. And so this is 0.56 and the minus the backgate bias. Okay. And so for the case of the previous page, let's say that if you put all the thickness in, M is 1.07, close to 1, but a little bit larger. If you put this 1.07 into this equation, you get VT about 0.08. Okay, and that's exactly this cross point, which is close to the linearly extrapolated intercept of the QI versus VG curve. Okay, so this curve is QI or minus QI. The QI is negative versus VG, and so this definition applies to the linearly extrapolated VT, more or less. And so that's, but of course you don't have to define VT. Okay? For this model, we just generate continuous curves. You can define whatever VT we want, but here we use this definition for convenience. Then in this case, VT is close to the intercept of QI VG curve. Okay. Also from here, you can see that there's a backgate control of VT, because this depends on the backgate through this term. Now M is close to 1, so the backgate effect is weak because T box is large. Okay. So just like bulk, the substrate substrate sensitivity, the threshold voltage reflected to the substrate reverse bias voltage is n minus 1 or equal to this. This usually is much less than 1. Okay? So you need a very large backgate bias to change the VT of the front gate through this expression. Okay, I covered a little more. Okay, move on. Now, so far we talk about the VG. Right? Let's see. Oh. Okay, so back to the numerical solution. Okay, the in this case, the V is 0. In other words, there's no VDS. Notice that there's actually V. The V comes in here, right? And coming in here. So if V equals 0, that's like at the source. Okay. But if you move from source to drain, then V will change from 0 to VDS. Okay. So in that case, we can generate a QI versus V plot. Okay. For fixed gate voltage, I show 3 curves. VGS go to 0.6, 0.81. Yeah. Of course, at the V equals 0, that's the intercept here to y with the y-axis. The higher the gate voltage, the higher QI at the V equals 0. But as for fixed gate voltage, if you increase V, in other words, if you move from the source to drain, then QI goes down, just like in bulk. In fact, it sort of follows this expression that we applied in bulk. Yeah? The C inversion, which is approximately Cox, Vg minus Vt minus MV. And those are the dotted line. The solid line is the numerical solution, and the dotted line is this equation. So more or less, it follows that until you are very close to so-called pinch off. Okay? So if you apply this, then you can get the current very simply, because remember that in bulk MOSFET we have the current is proportional to integration of QI from V equals 0 at the source to VDS, V equal to VDS at the drain. Okay? So if you use this or integrate, then we obtain this equation, which is exactly the same as bulk. And then, of course, the saturation, the ID set is given by that. And the VD set occurs in Vg minus Vt over M. So the only difference is M, the definition of M. For bulk, for bulk, M equal to 1 plus 3 Tox over WDM. For SOI, M equal to this, 1 plus front oxide divided by T silicon plus the back oxide. Okay. And then once you know M, then the current can be calculated. Okay. Now, okay, so so far SOI looks very promising. It's better than bulk because M is close to 1. If M is close to 1, you have a larger saturation current, and you also have a better, let's see, you also have a better subtotal swing. 60 M equal to 1 is 60 mil per decade. So it turns off fast, and when it turns on, it's a higher current. Okay. So that's why in the beginning, that's sort of in the middle 80s, it's like already 40 years ago, people are excited about SOI. But but unfortunately, SOI has drawbacks. Okay, and that's what we're gonna talk about, the drawback. And that due to short channel effect. And so far, we model SOI long channel MOSFET. But what about short channel? Just like in bulk MOSFET, chapter 5, long channel, chapter 6, short channel. Okay, so far, long channel looks good because M is close to 1. But when you go to short channel, that's a different story. The biggest problem with SOI shown on the right, if you look at the field pattern, is that compared with bulk, for bulk MOSFET, we assume that the diffusion region here is WDM is 10 nanometers. So this is fairly high substrate doping, and it's sort of like ground plane. So it's undoped at the surface, and then the substrate doping goes very high, like 10 to 19, so that the diffusion region, maximum diffusion region here is 10 nanometer. Okay, and then we use 1 nanometer. So for bulk, you can see the field. This is from this is based on numerical simulation, the TCAD simulation, and there's no field in the substrate because the field is only in the diffusion region. But for SOI, it's different because for SOI, you have a very thick box, buried oxide, where the substrate is very far away from the silicon film. So in this case, the field does not stop. It penetrates into the buried oxide. So that's the key difference. The field penetration into box, in this case, is a 200 nanometer, because this only shows about 50 nanometer. It goes way down. So in that case, we cannot have a good short channel model because in the bulk case, we say it's a rectangle with the left and right boundary is source and drain, top and bottom is gate and the substrate diffusion region. But in this case, there's no diffusion region. The field penetrates all the way to the substrate. So the so-called scale length model that we discussed for bulk MOSFET does not apply here. So we have to look at them numerically to solve this short channel effect. That's shown here. So let's consider these two cases. Okay. On the left is a bulk with a 10 nanometer diffusion width. On the right is the SOI, also with 10 nanometer T silicon, but no conductor after the 10 nanometer. This is the oxide. Yeah. So we can see that if you look at VT as a function of channel length, okay, SOI is much worse than bulk. Okay. So if you draw a okay, so this is what's the product here is the so-called VT roll off. VT roll off is the VT at whatever L minus the long channel. Okay, so by definition, VT roll off is 0 when the channel length is long, and when the channel length is short, it starts to go down. We call the VT roll off. Okay, so we define that we don't want this roll off to be worse than 50 millivolt. That's the dashed line here. So that means the minimum channel length for bulk is 29 nanometer, but minimum channel length for SOI is 58. That's twice, exactly twice. Yeah. So this shows that numerically, from numerical simulation, that this SOI has much worse short channel effect than this bulk. Both have a 10 nanometer, either the silicon thickness or the diffusion width. Okay. Furthermore, if you look at the surface potential minimum, again, this is the in a short channel device, in chapter 6, in the beginning of chapter 6, we talk about that the surface potential is lower in short channel than long channel because of the source drain effect of the source drain bands. Okay. And so for bulk, you can see that in a semi-log scale, okay, there's a constant slope. That's where this what we derived is exponential minus pi L over 2 lambda. L is the channel length, and the lambda is the scale length. Right? So that follows That's this dashed line here. But for SOI, there's no constant slope. In other words, you cannot define a scale length here. Okay. Okay. So for this case, okay, lambda is 12.6 nanometer. And that's the slope. And we again draw a horizontal line, 50 millivolts. For bulk, it's 26 nanometer. For SOI is 45. But more significantly, the slope is not constant, but length dependent. So that means that the scale length model is not applicable, simply because you cannot define a rectangle and solve the boundary value problem, like in the bulk case. One of the reason that SOI has a much worse short channel effect than bulk can actually be seen here. If you look carefully, these are constant potential contours. These labels are potential values, psi values. And so notice that in bulk, okay, potential is highest, which means the bending is highest at the front gate, because the VG is trying to bend the bends toward the surface. Right? So that's the largest surface potential occur at the front surface. For SOI, however, that's different. You can see that the potential actually increase. Okay? You see this potential decrease, which means that the surface potential decrease away from the gate. In this case, the potential actually goes up, which means that you have actually higher immersion charge. Notice that immersion charge density exponential function of the potential. Right? So when the potential goes up from, let's say, 0.3 at the surface to 0.4, the immersion charge rate goes up toward the back surface. In other words, in the SOI case, the potential on the back side is actually higher than the potential on the front side in a short channel device. Of course, that does not happen in a long channel device, and that's because of the effect of the drain, the lateral effect. Okay, so the back side is more affected by the drain in a short channel device. Okay, and we can see in this plot. Okay, if you just this is schematic plot. Okay, so this is the solid line is the energy band for okay, so energy band. Oh, okay. Let's consider this this solid line here. This solid line is VBS equal to 0, which means that there's no bias on substrate. That's this case. That's this case. Okay, the backside there's no bias, so we consider this curve. So you can see the potential actually or the band goes down, which means that you have a higher immersion charge density at the back than the front. Of course, the back is very far from the front gate, so that's why you have a very bad short channel effect, because the gate cannot control the immersion charge, which is maximum at the back side interface rather than the front side, like in the bulk case. we can solve that by applying a large substrate bias, like this red line. If you apply -20 to the backgate of VBG, then you pull this potential at the backside up. Then we restore the minimum, the potential maximum to the front surface. Okay? And so this is much easier to be controlled by the front gate. Okay. All right, so we'll take a 20-minute break, and then we'll resume at 10:10. Nice, it's 9:50. Okay. OK，继续上课。Andy，我的声音可以吗？
可以。
OK。So we talk about this chart. This means that if there's no backgate substrate bias in
唐老师
short channel, OK,
you close your PPT.
啊
You close your PPT.
，close
老
one，
师，你的 PPT 关掉了。
哦，等一下啊，看看，OK 吗
Yes.
？OK. So if there's no substrate bias, the inversion charge actually, the electron density actually higher at the back surface because the band is lower at the back compared with the front. Okay, this is a two-dimensional effect, as I explained earlier. Okay, so it's basically that saying that the potential is higher at the back surface, which means the band is lower, or electron density is higher at the back side. And that's not due to the gate voltage, but due to the drain voltage. Okay? In a short device, it will actually control the backside potential here because of drain bias. In the case where we apply a -20 volt to the substrate, then we'll change the potential, the band minimum or the potential maximum to the front surface. Okay, so this means that you have a better short channel effect if you apply a large reverse bias to the substrate. Okay. So if we look at the let's see, the minimum channel length defined here. The minimum, let's see, minimum channel length defined by the VT roll off equal to 50 millivolts. Okay, so this is for zero substrate bias. Okay, and for SOI, that's 58 nanometer. But if you apply a substrate bias, then it gets better, and that's shown in this chart. So if we apply a reverse bias, actually in this case fairly large because the box is very thick, it's 200 nanometers. So you have to apply something like 20 volts in order to reduce the L minimum from 58 to something like 43. Okay, and then it reaches a plateau. In other words, if you apply a reverse bias to the SOI substrate, okay, it will improve short channel effect for the first 20 volts, but then it stays the same to 80 volts. Okay, that simply means that once you have reverses, the further bias doesn't make the minimal channels any better until you have really very high substrate bias. That's like 100 volts. So what happened here is that it's explained here. That's because you apply, in this case, 80 volts. So from the band point of view, the back side actually becomes P plus. And the front side at threshold is N plus, right? The electron. And when the back substrate bias very high, that make the back side of the silicon P plus. Okay? So in that case, it becomes a conductor. Right? It's shown here in this case. Okay, and so now you can see the potential is confined in the silicon without going to the beryllium oxide. Okay, because the backside is P plus, which shield any field from the source and drain. Okay? So now it looks like bulk. Okay? So when you have the so-called backside accumulation, okay? Front side inversion, backside accumulation, and then that's why it becomes bulk-like, where the T silicon is the same as the maximum depletion width. Okay? And so after that, actually the approach is still not as good as bulk. Remember that for bulk, L minimum is 29. Okay. But we can get close. This is the 32, 33. Okay. So with the backside accumulation, we make the SOI behave like a bulk as far as short channel effect is concerned. But of course, in this case, the M factor, okay, is no longer close to 1. Okay, because now let's go back here. Remember in the for the long channel case, okay, we say M is equal to that. And where if T box is large, then M is close to 1. Because this is very small. But now I have a backside accumulation. Then the denominator becomes T silicon. So in that case, the short channel effect is better, but substrate swing is no longer 60 millivolts per decade. Okay? It's somewhat worse. So in the next chart, okay, we look at the substrate swing or inverse substrate slope, millivolt per decade. It's a function of channels. For with different substrate bias, 0 substrate bias, Okay, so this in this case, a long channel is close to 60 millimole per decade because M is close to 1. But short channel effect is poor. So you can see that it takes off when L is 20 nanometer. Okay? It starts with 60, but it goes up to 90. But if you apply a substrate bias, by the way, in this case the box is not 200 nanometer, it's only 10 nanometer thing. So you don't need very high reverse bias on substrate to have backside accumulation. So if you accumulate backside, M becomes larger. So further swing becomes 80 millimole per decade for long channel. But you can go to shorter channel without going up. You can see this one with no backside accumulation starts good, but it goes up sooner than if you start off with a larger substrate swing, but it goes to a shorter channel. So this is actually a better case once you talk about the short channel, because long channel substrate swing is not important. It's a it's a short channel device that we want to use. Okay? So in this case, for a 20 nanometer channel length device, this one, the backside accumulator is got a better, stays at 80. The other one goes up to 90 or even more, and it takes off. Okay, so now let's try to do some empirical modeling about the short channel effect in SOI. Basically, we try to use the scale length concept, but the scale length becomes a function of L. And we go back to this short channel curve. Okay, for bulk, it's the same slope. Okay, so lambda, the lambda is independent of L, but SOI, the slope keeps changing. So when we can consider that as a lambda as a function of L. Now there's a way to extract lambda, because based on the short channel model in chapter 6, the potential, the lateral field, okay, or the potential in the y direction, in the channel length direction, is given by this function, which has a lambda in it. In other words, it's supposed to go exponential, pi by over lambda. So if we look at different channel length device, we can look at the slope, and we say that using the slope, we can extract a lambda. Okay? And the result is shown here. So extract the lambda as function of L using the lateral field method. Okay? We obtain this plot. And so if you fit the lambda, it's something like 13 nanometer for this thickness plus 0.18 L, and that's empirical factor. Okay, and okay, that's the dotted line. The actual case actually it goes down like that, but that's not important, because once it's below 50 nanometer, then this is the short channel effect is too large. So these devices are not very useful because the severe short channel effect. Yeah. So largely it follows this line, and that all this can be empirical fitting can be summarized here. This number, this T silicon plus 3T-ox is the 30 nanometer. 30 nanometer is this. Okay, and then we say that L min equal to 2 lambda. lambda is given by that. So from that you can solve L minimum channel length given by this vector, where K is a range between 2.1 and 2.5, depending on whether you apply the substrate bias or not. Okay, so this is like the empirical effect of minimum channel length for SOI. Okay, so that's the okay. So we go back to this case. The initial schematic. We start with bulk. We need doping to define maximum diffusion width to control the short channel scale length. And for SOI, the long channel is fine, but short channel is bad because of field penetration into the barrier oxide. Even though you don't need doping here. But the ideal structure is actually double gate. Okay, so in which that you also have a T silicon. So that's just you don't need doping here, but instead of a buried oxide, you have another gate. Okay, so that the field is confined. Okay, so this one should have reasonably good short channel effect than the SOI case. Okay, so the next topic is double gate. Okay, so this shows, but the question is, how do you make a double gate? There are different configurations. If you can make the gate on top and the bottom, and this is the silicon wafer. But how do we make sure? But there are requirements because the gate has to be self-aligned. Remember that now the top gate is easy to self-align, but how do you self-align the bottom gate? The next configuration is that the two gates are left and right, and the source drain current is vertical. It's perpendicular to the wafer. Okay. This is so-called a vertical MOSFET. The third configuration, the gate is also left and right, but the source drain current is parallel to the wafer plane. And this is the so-called FinFET. And of course, we know that FinFET is the one that made the production, okay, not the top, bottom, or vertical MOSFET. And the reason is stated here. So what's the fabrication challenge of double gate? The front gate and back gate must be self-aligned to source drain and of course to each other. The second one is important. The silicon film thickness must be better than the minimum gate length divided by 3 or so. This we will talk about scale length later, okay? But basically requires, because in the let's go all the way back. In the double gate case, you don't need doping, but T silicon needs to be thin. Otherwise, compared with the minimum channel length, otherwise you have too much short channel. Okay. So if we go back to the FinFET case, so you want to make a FinFET, this silicon film has to be thinner than the minimum channel length, or the minimum channel length over 3, such as here, gate over 3. So that's a problem because usually the minimum channel length MOSFET is fabricated with the to the push lithography to the limit. In other words, the shortest length you can resolve, you can print on the wafer. That's the minimum channel length. But now, the film thickness has to be less than the minimum channel length. So in other words, we cannot make this FinFET with lithography. Okay, this thickness is below the resolution of lithography. So let me show the next chart. So this is the Intel announcement. They call it Tri-Gate because the gate actually goes, this looks like a FinFET. This is a fin here, and the gate goes left and right. There's actually a little bit of the top of the silicon film is controlled by gate 2. That's why they call it Tri-Gate. But essentially it's double gate because the top region is very narrow. That doesn't carry much current. The most of current is carried by the left and right surface area. And so they succeeded in getting this to manufacturing at 22 nanometer node. Okay, so after that, of course, we know that the industry has followed this approach. So for high performance logic, instead of bulk, the industry moved to FinFET. Okay. This, of course, well, first the lithography. Okay, lithography actually problem can be solved by this approach. This is so-called sidewall image transfer, or SIT. This is the IBM patent about 1980. So that's actually for bulk, but this shows you how to make a line beyond the lithography resolution. Okay, so basically, you put on some film on a wafer, and then you put another CVD film, conformal, and then you directionally etch this CVD film so that this film on the top, on the planar surface, is etched out. What's left is the edge, what we call the sidewall, because of the topography created by the first film, the edge of the second film is thicker at edge. So when you get rid of the film, the second film, on top and the bottom, you have sidewall left. And the sidewall is less than the minimum lithography. So it's those sidewall that you need. So the next step, you strip out the first film, and you have the two sidewall left. And that sidewall can be used to etch the gate or whatever, the fin, the silicon film, not the gate, silicon film underneath. Okay, so you use those sidewall as mask to etch. So in this case, the line width can be sub-lithographic, and that's so-called sidewall image transfer pattern. Okay? So pretty much all the company has followed this approach after Intel succeeded in production of such a technology. It's still tedious because first of all, you create two film, and the two film are connected. So you need another mask to strip out the connection in the other direction. But nevertheless, that's how the FinFET technology becomes manufacturing. But this point out another issue, and that is the multiple threshold voltage. In chapter 8, we'll talk about details, but basically you need the different threshold voltage for different circuits. Now, for double gate, let's go back. Okay. For this device, there's no doping in the silicon film, so the only way to control the threshold is by the flat band, by the gate work function. But how do you have multiple threshold voltage? You cannot. Okay, it's very hard to have multiple gate deposition for a different part of the wafer. So this point is just saying that how do you adjust the threshold voltage? Well, you can still put some doping in there. And so, for example, I forgot the silicon thickness, but you need something like I-1018 to shift the VT by about tenths of a volt. So this is diffusion charge density, QNAT silicon in the silicon for this doping, and then divided by 2 Cox, because the diffusion charge is shared by 2 gates. Okay, so only half of the diffusion charge goes to one gate, and the other half goes to the other gate. So if you put this much doping in the thin silicon fin, then you can shift the threshold voltage either up or down by tenths of a volt, depending on the doping polarity. And so this can be done. But what's the best benefit for double gate? Yeah. Okay. This is the best benefit. It's 60 milliohm per decade. Okay. In other words, M is always 1. And to see that, we go to we go to this chart. Okay. So this is M. If there's a front gate, this is for single gate. Okay, so you have a single gate. This is either bulk or SOI. You have a substrate, and that doesn't change. But now you have 2 gates. In other words, you move the gate voltage both on the left and the right. So of course, if you move this horizontally downward, then the surface potential is the same as the gate on the front and the back. So M is 1 if you have a double gate. Okay, so in other words, the other side is no longer grounded, but rather connect to another VG. Those VG are the same. So when you can you change both VG, you change both points up and down, that will change the surface potential by the same amount. So that's why M is always 1. Okay? So this actually is the best, best benefit of a FinFET or double gate is M equal to 1. So now you can turn it off. If the threshold voltage is only 0.2 or even below, you can still turn it off. In bulk, you are stuck with 80 millivolt or 90 millivolt per decade because M is 1.3 or larger. That's controlled by the doping. All right, so let's talk about the model for a symmetric double gate, which means that the top and the bottom gate have the same work function and connect to the same gate voltage. So VGS top and VGS bottom. and the source drain is in the other direction, and the silicon film, well, in terms of film fat, it looks like this. This is a cross section in the perpendicular direction here. So this film fat is gate goes like this, and that's the T silicon, T ox. Okay, but it's easier to analyze this way. So we define 0 to be the center of silicon film at the source. X is in the depth in the thickness direction. Y is in the source drain direction as before. And so X can go from minus T silicon over 2 to plus T silicon over 2. Y can go from 0 to L. L is the channel length. Okay. So we have a Poisson equation. This is a GCA model, so there's no Y curvature. Okay? And it's undoped, no diffusion charge, or the diffusion charge is assuming it's negligible. So there's only mobile charge given by that. And boundary condition. Okay, boundary condition is the same as the SY case. But in SY, you have two, front and back. In this case, it's the same because it's symmetric. Okay, so only one boundary condition because it gives you the same answer. Right. So this is a second order differential equation, but with only one boundary condition. That's because of symmetry, because psi is symmetric with respect to x equal to 0. Okay. Now what's the d psi dx is 0 at x equal to 0. Okay. And this is defined before. Okay. So schematically, we can look at the band like this. Okay. The left band diagram, Vg equals 0, that's below Vt. If it's below Vt, there's no charge. There's no diffusion charge because it's undoped. And the emerging charge is very small. It's below threshold. Okay? So essentially, the band are flat. And now, so what determines the where the EC and the EV are? Well, it depends on the work function. You can see that the work function, okay, you go up from this. Okay, so this is the Fermi level of the source. If this is Vg equal to 0, so gate Fermi level is the same as the source Fermi level, right? And that's the gate work function. That's the free electron level or the free. And then you go down from that. That's the conduction band. That's the electron affinity. Okay. So that's all fixed. Okay. So the band is fixed by this condition. Okay. And yeah, so there's no contact with the silicon body, so the band is dictated by the gate work function. And I just showed earlier in the SY, earlier today in the first class, that even with slightly doped, the effect of the diffusion charge on the band is negligible, assuming the silicon is not thick. It's like let's say 10 or 20 nanometers. So body may not be charge neutral. Okay. Because the Fermi level of the band condition is completely dictated by the gate and source and drain. Okay, so that's a 0 gate. Now, on the right, we apply a gate near threshold. condition, and we consider a bend diagram near the source. All right, so now, by the way, just in case you wonder how the bend moves, okay, the VG will move the gate Fermi level with respect to the source Fermi level. Source Fermi level is fixed, this dotted line. So if you apply positive gate, it goes down. If it's still subthreshold, then the bend will just move with it. Remember that m equal to 1, so there's no there's one-to-one correspondence between gate change and the potential change or the bend change until you have an inversion charge. Okay. Once you are near a threshold, you can see that you bend this band so that the conduction band is close to the source Fermi level. So now we have a inversion charge at both surfaces, the symmetric. Okay. So now we have a curvature controlled by this expression here. So now the mobile charge, the electron density becomes appreciable near either surface. Okay. And that's when this the MOSFET turns on. I think I explained everything. Yeah. So other than mobile charge, before threshold, the bands are flat, whether VGS equals 0 or not, as long as in subthreshold. Only when you go near threshold or above, then you have a band bending here. Okay. Oh, okay. This is a chart that we have in chapter 4. Okay. Just try to remind you in the ball case where we have the Poisson equation has a fixed charge due to depletion charge of dopants and a mobile charge. And we can integrate this equation once, okay, of this dψ dx, square root of all that. But then we cannot integrate again because this function is the square root of this very complicated function. Okay? So we cannot integrate. But with double gate, there's no fixed charge, only mobile charge. In this case, actually, you can solve it. It's shown here. Okay, so that's the same Poisson equation, second order, mobile charge, electron only, because the whole density are negligible. And this fixed charge is also negligible. And this is a GCA model. Okay. So this equation actually has an analytic solution. Okay. So we have to go back and look at some of the math. By the way, there's a parameter called V. Okay. V is the electron quasi-Fermi potential. So V will change from 0 at the source to VDS at the drain. But V has no X dependence. Okay. So as far as the differential equation for X is concerned, V is a constant. Okay. Just like any other GCA model. For a vertical slice, V is constant. So we can solve that second order differential equation in the X direction. So I have some charts to show how this is solved mathematically. The first one is easy. So just like in the ball case, we can integrate once, get dψ dx. Okay. So we do the same thing, multiply this, and then we solve dψ dx. Okay. Introduce a integration constant. We go to C. Okay, now to integrate again, remember that V can be treated as constant as far as X is concerned. we replace the function psi with the function u defined this way. Okay. So that the first term under the square root is second square. So second square minus 1 is tangent square. Square root of tangent square is tangent. So this equation is simplified to this form. Okay. And then d psi dx can be converted to du dx and all that. So it becomes a very simple first order differential equation u du dx. So u is linear in x. Okay. And so we can go back. If you know u, then we can solve for psi. And that's here. Okay. The c is the integration constant. There's only one integration constant. That's because even though it's a second order differential equation, but it's symmetry. It's a symmetric double gate. Okay, so only one showed earlier. Okay, only one boundary condition. So only one integration constant. Okay, in this case, we call it beta here. In the derivation, we call it c, but c and beta can we can define. Okay, we can transform the c to beta by defining this parameter, and we obtain the psi as a function of x. Let's see, x here, log cosine, and beta is a constant. Okay, everything else is v is the depend on where you are. At the source, v equal to 0. At the drain, v equal to vds. In between, it's governed by the current continuity equation. Okay. And so what's the equation to solve beta? Okay, beta is given by the boundary condition by this boundary condition. And again, we can derive that. After we solve this, the boundary condition, we put the psi solution, and also d psi dx becomes beta tangent beta, and then we can put it back here. We obtain this equation. So this equation is the equation to solve beta. That's the replace the initial boundary condition, and it depends on v. Okay. In other words, beta depends on v, which means that beta changes from source and drain. Okay. So we will go back to here. So v varies in the y direction. So is beta. Beta is also varying from in the y direction from source to drain. And we call this beta s and beta d. Okay. So beta s is solved by letting v equal to 0. That's the source. So v equal to 0 at the source, and we solve this implicit equation. That's called beta s. And at the drain, v equal to vds. We solve it again, and that solution we call the beta d. Yeah, so beta s and beta d solved this way. And then we can get the current. Let's see. Yeah. So the source beta s, beta d. And one more derivation. is from the current continuity equation. So IDS equal to that we derived in beginning of chapter 5 still works. And in this case, we change the integration from V to beta because the beta is everything is in terms of beta. Okay. And QI, which is remember that's the that's related to the field. Let's see. Okay, that's QI. The front and back. Front and back are symmetric. So when you invert both surface. Okay, so that's why you have this QI factor of 2. Factor of 2 comes in. Okay, that's the front and the back. The two channel you turn on both surface. Okay. And so we can put everything in terms of beta in here. Okay. dV d beta is this function. Qi beta is this function. Okay. And then we integrate. That's this equation. This actually can be integrated analytically into this form. Okay. And in front is just a constant. But integration, original integration is 0 to BDS. Once you change to beta, it's from beta S to beta D. Or beta D to beta S, you want to make it a positive. There's a negative sign somewhere. Okay, so that's where the solution is. So let's go back to this expression. The analytical solution to the original Poisson equation is here. Okay, it's function of x with a parameter beta dependent on v. Okay. Given by this equation. Okay. This equation is a one-to-one correspondence between beta and v and beta. And then IDS becomes this function. So to calculate IDS, you just have to calculate beta S and beta D. Once you have beta S and beta D, you just put in this integrated bracket here and then get the IDS. Yeah. The range of beta is between 0 and pi over 2. Okay, because let's look at this equation. Okay. VGS VGS minus V, this can be negative or can be positive. Okay. So left side can go from minus infinity to plus infinity. The right side, if beta is 0, then it's minus infinity. Because log 0 is minus infinity. Plus infinity is beta equal to pi over 2. If beta is pi over 2, tangent beta is infinity. That means right side is infinity. So the range of beta is 0 to pi over 2. And that will solve any gate voltage, VGS minus V. Okay. That's the range. So okay. We'll talk about next chart first. It's easier because I just described. So we define this f and g. Okay, f is this log function. G is this. If we go back to f is this function, the log beta minus log cosine beta. G is the function for the current. And then So the only parameter here is this alpha, which is at RR. That's constant, given by the thickness and the dilution constant, okay, between silicon and oxide. Okay, so you can generate a plot of if you change beta, you get a F and G. Okay, so you can plot G versus F. Okay, we have it's the same function but two scales. This curve uses the linear scale. This curve uses the log scale. Okay, this is for the subthreshold. Okay. And so all you have to do is to find out the value for a given gate voltage. For a given gate voltage, you can solve a function, solve this for that's beta s here. And for that gate voltage, if we know VDS, let's solve for beta D. And once you know beta S and beta D, IDS is simply the difference between the G value. So G of beta S minus G of beta D. That's the current. Okay. All right, we take a 10-minute break and then we'll resume at 11:10. So this shows how we can use the function f and g of beta. Okay. F and g of beta to construct to find the value of IDS for any given VGS and VDS. Okay, so first, for a given VGS, we find out the beta S from this G versus F curve. Okay. So let's say this one is the value of F beta S. So in other words, F beta S equal to 20, 21 or something like that. And then G is either the log scale or the linear scale, right? Equal to that value. And then for VDS, so beta S only depend on VGS, but beta D depend on both VGS and VDS. And that's this point. Of course, this F is much less. Okay? You can see the F goes from 21 to 8 or something like that. And the corresponding G is much less. And then the difference between the G beta S and the G beta D is proportional to the current. Yeah. This graphical depiction of how we solve the IV curves from this, I call it analytic potential model. And now I want to talk about one particular thing about the double gate, and that's so-called the volume inversion. Okay, the volume inversion was published in a very early paper in 1987. Okay, this claims that we go back to the double gate picture. Claims that since we apply VGS to both gates, so you turn on both sides, they consider that the whole silicon film is inverted. That's why they call it volume immersion, as opposed to surface immersion in MOSFETs. Okay. But that's sort of misleading, as shown here. So here's a solution of potential and the electron density. Potential, solid line. Electron density, the right scale is the dotted line. And that's a silicon film. The gate is, in this case, is a 20 nanometer silicon film. So there's a gate at a -10, and a gate, the gate is beyond oxide, whatever. The oxide is 2 nanometers, so 2 nanometer beyond the silicon surface as the gate on both sides. Okay. And so we have 3 gate voltages that will corresponding to side 1, side 2, side 3 as a function of x. Okay. The corresponding electron density is shown here. Now, you can see for side 1, it's very close to volume immersion, okay, because essentially the whole film has more or less the same electron density. But as side go to side 2 and side 3, it becomes N2 and N3. In this case, there's no more volume immersion. So the volume immersion actually only occurs in subthreshold. Okay, because once you have immersion above threshold, then electron density is so high that it's no longer uniform. Electron density is no longer uniform, like in N3 case. Okay. Another way to see it is that the immersion channel at the both surface screen the gate field from the center. So the center electron density is never very high. Okay. In fact, if you plot, let's see. Let's consider the 20 and 2 case. Okay, so let's call this the solid line. Okay, we consider psi 0. That's the potential at the center, and potential at the surface, psi 0 and psi s. So you can see that psi 0 has a maximum value. Okay, even if the gate voltage go very high, the center can the potential is limited. There's an upper bound given by this parameter. This can be seen easily from an analytical solution. Okay. So psi 0 means that x equal to 0. X is 0. Cosine 0 is 1. Log 1 is 0. So this term is 0. In that case, it's given by, so at the center, the potential is given by that. All right? So it depends on beta. The beta inside the log. Okay? But beta cannot exceed pi over 2. So the maximum center potential is given by beta equal to pi over 2. So if you let beta equal to pi over 2, with the last term go to 0, and that's the maximum center potential that's given by this. Okay. And that shows the psi 0 is limited. Okay. Psi s, on the other hand, keeps going up, as shown here. Okay. So the center stops increasing with gate voltage, but surface keeps going up with higher and higher electron density. And that's because of this term. Okay? So when at the surface x equal to T silicon over 2. Right, so this is cosine beta. Cosine beta. If beta equal to pi over 2, cosine beta is 0. Log 0 is minus infinity. So this is actually infinity. So there's no upper bound for surface potential, but there's upper bound for center potential because there's no third term when you talk about center x equal to 0. Okay? And that's why there's a upper limit. Yeah. And to increase our upper limit, you have to decrease the T silicon. In this case, 20 to 5. Then the size 0 will go up, like shown in the dotted curve. So this means that the so-called volume inversion doesn't really help. It's still, once you turn it on, it's still surface potential. It's a surface channel, two surface channel. We'll say that even more clear later on when we talk about the regional solution. Okay, so we can generate the IB curves. This is IDVG and this is IDVD from the analytical potential model. And this model is continuous from subthreshold to the parabolic region to saturation. Okay? This only all regions are covered with one under one continuous function of G versus F. Notice that for bulk, we have to derive different regional solutions for below threshold and above threshold. But for double gate or symmetric double gate, we can actually generate different regions with one solution that we just talked about. Okay. So let's look at IDVG. IDVG product in linear scale and log scale. Okay, so linear scale, you can read the above threshold. Log scale, read the below threshold current. And there are two devices, same oxide but different silicon, 25 nanometer and 5 nanometer. Notice that the both thickness produce the same result, above threshold, but subthreshold is different. 25 nanometer is higher than 5 nanometer, and this is due to volume inversion. Okay? So volume inversion, the 25 nanometer is 5 times larger than 5 nanometer, and this is exactly a factor 5 difference in subthreshold. But there's no volume inversion above threshold. So even though thickness is 5 times larger, the current is the same, whether you have 5 nanometer or 25 nanometer thickness. So T silicon only made a difference in the off current. Okay, we can see this even more clear by looking at the regional solutions. This IDBD is simply you first, for given VG, VGS, you can solve beta S, and then for each VDS, you solve beta D, and then you get a current. Okay. So next, we try to look at the regional approximation of the analytic potential model. Okay. some people call the beta model. So in other words, that's the model. Right? Only one function cover all regions. But now we apply different approximations so that we can generate explicit, because this is implicit equation, okay, of beta S and beta D. But to get explicit, we have to use regional approximations. So first we consider, remember that the beta range is 0 to pi over 2. And the f function, the 3 terms, log beta, log cosine, and beta tangent, above threshold. Now, the left side is this f VGS minus V0 minus V. And this usually is a large voltage, let's say 1 volt. And then divided by 2 kT over Q. 2 kT over Q is only 50 millivolts. Okay? So this is much larger than 1. So in that case, the dominating factor term of those three is beta tangent beta. Okay, because this, when beta approaches pi over 2, this can go to infinity. So this can be large. But these two are limited. When beta equal to pi over 2, log pi over 2 is not very large. In this case, when beta approaches, so when beta approach pi over 2, if beta approaches 0, this is cosine beta is 1, log 1 is 0. So it approach pi over 2, then cosine beta equal to 0. This can be large, but this one goes much larger because this one is a log factor. Okay. There's 1 over cos, this is essentially 1 over cosine beta here. So if we approximate f by the last term, okay, then we can solve beta, explicit function. And we make beta is pi over 2. So this beta is pi over 2, but this tangent beta is given by this gate voltage. The higher the gate voltage, the closer beta is to 90 degrees. In the meantime, the G function, which also has 3 terms, will be dominated by the last term, beta square tangent square. So the first equation gives you beta tangent beta. The second equation is the square. Right? So IDS is the G. Let's see. Is G beta S minus G beta D. G beta S is beta S V equal to 0. Right? So it's VGS minus V0 square, because this beta tangent square, the square of the upper equation, minus beta D, G beta D. And G beta D is the square of that, with V equal to VDS. Okay. So from here we obtain, in this case, the above threshold linear region, IDS equal to that, where we can see that it's very similar to the bulk case, with the M equal to 1, V0 is like threshold voltage VT, and the factor of 2 comes from the fact that we have 2 channels, 2 gates, and therefore we have 2 channels, doubled current. then okay, it's given by this. So okay, but there's an issue here. That says this V0 here is a T-silicon dependence. But we know from numerical solution that above threshold curve is independent of T-silicon. And T-silicon changes by a factor of 5, but the curve doesn't change. So we try to answer the question of why the V0 has a T-silicon dependence, but actually the actual result should not have any T-silicon dependence. And the answer is from the second order term, because we only keep the first order term in this chart. So the first order approximation, we only keep the last term. Okay, so if you want to make a correction, you keep the second term. Second term is log beta. The first and second is beta over cosine beta. So if you make a second order correction, then you will see that the so-called VT that's V0 plus this term, okay, with beta set equal to the first term. And so you can see that the T-silicon, if you take only the first order term, as a T-silicon as a dependence in the log. But this term has a T-silicon dependence in the numerator. So when you add them together, the log is the product of this one and this one. So T-silicon will cancel. Okay. So this means that if you do a second order correction, there will be no T-silicon dependence. And that's why. So that explains this this point, why the result is independent. But if you take the first order, it appears that it's dependent. But the second order, if you include second order, it's still T-silicon independent. Okay. So this is approximation in the above threshold. Below threshold, subthreshold. Subthreshold means that the f function is negative, okay, because VGS is below V0, so it's negative. If it's negative, then the beta is close to 0, and dominant term is log beta. Okay. So both beta S and beta D approach 0, and only the first term log beta is kept. Okay. So now we can solve explicitly beta S and beta D. Beta S V equal to 0, beta D V equal to VDS. At the same time, GR is the last term is negligible. When beta approaches 0, tangent beta is beta. So beta square minus beta square over 2. You end up with beta square over 2. Okay. And beta is exponential of that. And so beta S is exponential of QVGS minus V over 2KT. And beta D is this minus VDS over 2KT. And then G is beta square. So you square that, this 2 will disappear. Okay. So the current, there's a closed form of current in subthreshold. And it looks like that. And again, we have the same VDS dependence as in the bulk case. In other words, once VDS is above 50 millivolts, the subthreshold current becomes VDS independent, okay, because this is essentially 1. And it's exponential. And it's notice that there's no M because M equal to 1. So in other words, you always get 60 millivol per decade slope. Okay? In fact, you can get this just from diffusion equation, simple diffusion equation. Okay? The dn dx times diffusivity, which is mu times kd over q, mu kd over q, and dn dx n is the electron density of the source minus the electron density at the drain divided by L. Okay? And yeah, okay. So if you summarize what we have from the two functions f and g, okay? In the linear region, both beta are close to pi over 2. Okay? In subspecial, both beta are much less than 1. Okay? Saturation, beta s is close to pi over 2, but beta d is very small because VDS is large. Remember that okay. In saturation, okay, so beta s is close to pi over 2, but VDS is large, so that beta d is actually much less than or close to 0. Okay, and so we can see the saturation expression here. The I include a term here. This term is the second order term. Okay? It's small compared with this, but it shows that it goes down exponentially as a function of VDS. So when VDS go to infinity, this one go to 0. So this means that if you look at the IV curve, okay, let's look at this curve. So essentially approach the saturation continuously. So in other words, it's asymptotically approaching the saturation current with one continuous function. With one continuous function like this. And all right, so two key points. In subthreshold, this current is proportional to silicon, but independent of Tox. Okay? This, of course, is due to volume immersion. Why is it independent of Tox? Okay, we can go back to this picture. If it's subthreshold, the bands are always flat. Okay? So when you change the gate, the band just move with it, regardless of how thin or how thick oxide is, as long as there's no charge. Right? If the charge is negligible in silicon, then when the gate voltage change, the band will follow exactly, independent of Tox. So this explains basically why we get this. So you can see this property silicon, but independent of Tox. The second point is above threshold, either this one or this one. It's proportional to Tox. That was proportional to 1 over Tox. But independent of T silicon. There's no T silicon in the first two cases. Only 1 over Tox. And this also can be understood physically from this picture. once you are above threshold, the center region doesn't contribute to any current. It's only to the surface. So it doesn't matter how thick or thin T silicon is if you are above threshold. Below threshold, you have volume inversion, so T silicon matters. Like we explained here. So above threshold only depend on Cox. Only depend, in this case, Tox is the same. Okay, so there's only one curve, even though you have two silicon thickness. But below threshold, the current is proportional to T silicon. As described by this expression here. Okay, so so this is the long channel model for symmetric double gate MOSFET. What about the short channel? Scale length. So we can follow the same approach as the bulk in the bulk short channel effect, the scale length model for bulk in chapter 6. We solve the 2D Poisson equation. Okay. In silicon and in oxide. In this case, I include a doping Na, even though it's not important. Okay, but I just include it for general purpose. If it's lightly doped, then you can set Na equal to 0. And for oxide, so this psi is for silicon. Psi with a superscript of plus minus is for oxide. Plus is for one oxide, minus for the other oxide. Okay. And then the boundary condition on the two gates. Okay, two gates is the psi equal to VGS minus the fat band. It's a work function difference. At the source, okay, x0 is Eg over 2q, that's n plus. And drain is Eg over 2q plus VDS, just like in the bulk case. N plus drain bias at the VDS. And the dielectric boundary condition between the potential in silicon and the potential in oxide is that the potential, okay, so now at the interface is x equal to T silicon over 2 plus minus T silicon over 2. Okay, y is anything. So the potential, these two potential functions must be continuous at the dielectric interface boundary on both sides. They're the same. And also the displacement. Displacement is applied to the field or derivative of the potential. Okay. And so the derivative times the permittivity in silicon equals to the derivative in oxide times the permittivity in oxide. Okay. And so these are the two boundary conditions. And just like in bulk, we can also obtain a scale length equation. Basically, we try to use the superposition. So for silicon, we have three terms. Vx, that's for long channel. Us and UD, that's to satisfy the source and drain boundary condition. In oxide, the psi plus minus also has the long channel and then the two US plus minus and UD plus minus. Okay. And the long channel solution is given by this here. There's nothing special. It's just this essentially. Let's see. This is all subthreshold, of course. Okay. So there's no mobile charge density. No mobile charge density, that's easy. Okay. That's sort of like this. There's no curvature due to inversion charge density. Okay, that's V. And this is depletion approximation. Okay, so this is basically a parabolic curve if doping is Na. If Na is 0, then you only have one term, or VGS minus 5Mi. That's it. And in the oxide, it's linear. And so basically, that describes this function. Oh. Okay. And then, well, if Na is 0, then oxide is constant also. You can see that if Na is 0, then these two are the same. Okay? But in general, I kept Na in the solution here. And then the USUD are here, which basically are like the bulk short channel model. Okay? So so they have to vanish. Let's see. They have to vanish at they have to vanish at top and bottom. Okay, top and bottom is this. Plus is top, minus the bottom. So in other words, here, US. So when X equal to T silicon over 2 plus Tox, that's top and the bottom. Okay? Because X equal to 0 is the center. X equal to T silicon over 2 is T silicon over 2 is the friend surface, and then plus Tox. So the friend gate is T silicon over 2 plus Tox. Okay, that's where this from. T silicon over 2 plus Tox. And they have to go to 0 because of the sign. Now for the silicon part, US and UD, we use the symmetry because this is a double gate. So the potential is symmetric in with respect to plus minus X. Okay, so which means that the field of d psi dx has to be 0. So basically it's a cosine with no phase angle because the cosine is symmetric, whether X is plus or minus. Okay? Or if you take a derivative, becomes sine. And sine X is 0 if X equal to 0. And so the field is 0 and potential is symmetric. So that determines that. The rest are the same as in bulk. The US, it's 0 at the drain. UD is 0 at the source. And because of the sinh and sine cosine with the same lambda and lambda, so every one of US and UD will satisfy the Poisson equation with 0 charge. In other words, it satisfies this equation equal to 0. Because one is sine cosine, the other is sinh. Okay? So they add up to 0. That's like in the bulk case. So we apply the dielectric boundary condition to this solution, and then we obtain the scale length equation, and that's here, given by. So the scale length equation for symmetrical double gate is this for lambda. Again, we look for the longest solution of lambda. That's the scale length for the double gate case. Okay, so that is two tension product equal to the ratio of permittivity between oxide and silicon. Okay, now in this case, so it's tangent of one angle and tangent of another angle, okay? And their product is positive. So both angle is in first quadrant. If both angles are in first quadrant, then that means that pi tx over lambda is less than pi over 2. Okay, so that means tx over lambda is less than half. Okay? You can see that the tx over lambda does not go above 0.5. This one is less than pi over 2, which means that the lambda, the T silicon is less than lambda. Okay, so T silicon over lambda is less than 1. Okay. So that's the solution of this eigenvalue equation. And again, we can look at some special cases. One, that's when the two dilute constants are the same. If two tension product equal 1, that means the two angles add up to 90 degrees. Okay, so if tension A times tension B equal to 1, then A plus B is pi over 2. So if this plus this is pi over 2, then lambda is solved. T silicon plus 2Tx. Very simple. And this we go back. T silicon, if epsilon oxide and epsilon silicon are the same, then the total distance from top gate to the bottom gate is T silicon plus 2Tx. One Tx on top, the other Tx at the bottom. So this lambda is simply the physical height of the region between the two gates, from one gate to the other. Okay, so that explains this simplest straight line here. At the lower right corner, okay, Tx is much than T silicon. In that case, the first angle is close to 0. Second angle is close to pi over 2. Okay. So we can again approximate, and then we obtain the lambda solution here. It's T silicon plus 2. Okay, so in this corner, 2 epsilon silicon over epsilon Tx. And okay, so in this case, if you have a high K, that helps, because if your epsilon oxide is high, that makes this small, which means the scale length is small, but it's still limited by T silicon. Okay. So in any case, lambda is larger than T silicon because T silicon over lambda is less than 1, and lambda is larger than 2Tx because Tx over lambda is less than half. Okay, and so after you determine the lambda, then minimum Taylor length is about 2 lambda, the same as in the bulk case. So this is the scale length model for short channel double gate MOSFET. And you can see why the T-silicon is important, because T-silicon comes in here and here. So that justifies what I said earlier of the requirement. Why the silicon film thickness must be less than over 3, the minimum gate over 3, so that the scale length is less than L min minimum channel length over 2. This is roughly, because in general, lambda is larger than T-silicon, right? Because T-silicon minimum value of lambda is T-silicon. So 2 lambda is larger than 2 T-silicon plus something. So we make it 3 T-silicon. That's why I say T-silicon minimum maximum is L over 3. All right, so this gives you 2 and the other one is 3 roughly. Okay, so that's for double gate. Next, we're gonna cover the nanowire. Nanowire is similar to double gate, except that it's cylindrical. So in other words, it's a if you look at in this cross section, the gate goes around this. So you have a silicon wire, you grow oxide, TOX, and put gate all over. So this is also called a gate all around MOSFET. But if you take a cross section here, a cross section in the Y direction, Y is the source to drain direction. Okay. And so now we change from X to the polar, the rho, or the polar cylindrical coordinates. Okay. And R is the radius of the nanowire. Okay. And so the cross section looks like that. That's the radial direction. Y is again the source and drain. The R is the radius, so this is the diameter. And we apply Vs, or we say 0 to the source and then VDS to the drain, or Vs to the source and VD to the drain, same thing. And it's symmetrical in around. Okay, you can rotate. So in this case, the Poisson equation, we use cylindrical coordinates. So the curvature, the second order derivative looks like that. The right side is still the electron, the mobile charge density. Okay? And in this case, we have a symmetry condition is that psi is symmetric, so d psi d rho is 0 at the center of the nanowire. And it turns out that this also has this equation subject to this condition also has a analytical solution. It looks like that. Again, with a condition, with a boundary condition satisfied by this parameter beta. And then we have the boundary condition applied in the radial direction. In this case, a little bit more complicated, but it also produces an equation for beta here. Okay, so again, you have a beta S and beta D. Beta S is the solution to this equation when V equal to 0. Beta D is the solution to this equation when V equal to VDS. It's just like the planar double gate case. And then you can derive a drain current by integrating the current continuity equation. Current continuity equation is here. And after going through all the math, it becomes of this form. So this function at the beta s minus this function at the beta d, where beta s and beta d are the solution of this equation for the source and for the drain. Okay. So it goes in parallel with this symmetric double gate, except that all the equation is changed. Okay. But the principle are the same. Okay, so we're almost done with chapter 7. There's a couple of charts left. Okay, and we'll wrap it up in the next class next Monday. Okay, I've announced the midterm 2, which is 2 weeks. 2 weeks from today. It will cover 3 chapters: chapter 5, 6, 7. Okay, after the midterm 1. All right, I'll see you next Monday.